This is part one of a four-part mini-series in which we'll explore four different methods for handling 3D finite rotation. When dealing with geometric nonlinearities where moderate to large deformations and rotations can occur, the ability to accurately describe and compute finite 3D rotations becomes essential. We'll delve into the tools that engineers rely on to tackle these challenges. These include Euler angles, direction cosines, and Rodriguez rotation formula. And while quaternions play a prominent role in fields like robotics and aerospace, we'll only briefly touch on them as our focus is on methods most applicable to structural mechanics, and quaternions tend to be seldom used in structural mechanics. The first topic will be Euler angles, and Euler angles, as you might guess, were introduced by Leonhard Euler. And that shouldn't be surprising because in so many things in mathematics, Leonhard Euler had some involvement. Euler, who lived in the 1700s, introduced the concept of Euler angles in 1765, and in doing so, Euler provides a straightforward way to describe the orientation of a rigid body through three sequential rotations about chosen axes. Euler angles are widely used in structural mechanics because of their intuitive representation of rotations. So to understand Euler angles, let's first draw a set of three-dimensional axes, and we will label these axes x1, x2, and x3. And I guess this represents a slight departure from using the x, y, z symbols. And I like to use x1, x2, x3, as we can refer to our axes as x sub I, where I goes from 1 to 3. This is not designed to confuse you, but as you get onto more involved topics in structural mechanics, it's useful to have compact ways of writing things. Now we will assume that these axes are embedded within an object so that they're body-fixed axes. In other words, the axes themselves represent the orientation or attitude of an object. Now we'll assume initially that these body-fixed axes are oriented as drawn, and then what we would like to do is introduce a rotation. The idea is I would like to rotate this set of axes about the x3 axis by an angle that we'll call theta 3. In doing that, I rotate the axes into a new position, and I'll draw that in red just to keep it clear. So the x3 axis doesn't change because that's the axis of rotation. And this new reference frame, or this new set of axes, we will refer to as the prime set. So this red arrow would represent x3 prime, and of course x3 and x3 prime are in the same direction. But the other two axes will obviously rotate from their original positions, and we'll call these new axes x1 prime and x2 prime respectively. And just to make it clear, this is also rotated by theta 3, and same with the x2 prime axis, has rotated by theta 3. Just to make it a little bit clearer, and I'm going to do this first one painfully slowly so that there's no confusion at all. If I were to draw this in two dimensions by looking down the direction of the x3 axis, I could draw my x1 axis pointing straight down and my x2 axis to the right, and then the location of my x1 prime and x2 prime axes are as follows. And of course the rotation amount is theta 3. If I want to write x1 in terms of x1 prime and x2 prime, that I can do quite easily. x1 is equal to, it will be x1 prime times cosine of theta 3. This is the projection of x1 prime in the x1 direction, minus x2 prime sine of theta 3. Why is it minus? Because the component of x2 prime that's in the x1 direction is actually in the negative x1 direction, as drawn. Similarly, I can write x2 as, well, it will be x2 prime times cosine of theta 3 plus x1 prime times sine of theta 3. And why is this one plus? Because the component of x1 prime projected in the x2 direction is in the positive x2 direction. And then, of course, x3 is equal to x3 prime because both those axes point in the same direction. Let's give these some numbers, 1, 2, and 3. And now I can rewrite this in matrix form as x1, x2, and x3 are equal to some transformation times x1 prime, x2 prime, and x3 prime. We can see that that matrix must be cosine theta 3 minus sine theta 3 and 0, sine theta 3, cosine theta 3 and 0, and 0, 0, 1. And these are just the coefficients that I can pick off from equations 1, 2, and 3. We'll call that equation 4, and let's put a red box around that. So I suspect there's nothing really new for most of you about what I've done here. I've really just taken the 2D rotations we've been dealing with and I've expanded it to 3D. And really the only difference here is that we recognize that the axis around which the rotations occur, we put a 1 there, and the remaining elements in the row and the column gets a 0. For the other two coordinates, we get a cosine on the diagonal, and we get sines on the off-diagonal. Now, the cosines will always have a plus sign in front of them, and one of the signs will have a plus sign and one of the signs will have a negative sign. Here's a good rule of thumb that you'll never mess up the signs again. If I am writing x1 in terms of the other two axes, because x1 is outside the two red axes, it's going to carry the negative sign. So the row corresponding to x1 will have a negative on the sine term. Because x2 is in between the other two axes, it will have a plus sign on both terms. So the sine and the cosine terms for x2 will be plus. If you just remember that rule of thumb, you'll never mess it up again. You've got a 1 corresponding to the axis of rotation, and zeros for the row and the column corresponding to the 1. Then the remaining two diagonal terms are the cosines, the off-diagonal terms are the sines, and depending on whether the axis is in between or outside the other two axes, the one outside will get the negative sign and the other one will get the positive sign on the off-diagonal term. All right, I think we've beaten that to death. Now I'm just going to delete this and scoot it up just so we can make a little bit extra space here. There. I really just want to try to get all of this on one page because I think it will be far more informative that way. Now we proceed by applying a second rotation. And that second rotation is going to be about one of the red axes. Not about the x3 prime axis, obviously, because we've just used that one. So it needs to be about one of the other two, either x1 prime or x2 prime. Now, in general, we can assume that the initial axes, the black axes, represent an inertial reference frame, like a ground-fixed frame, and that the Euler angle rotations are going to tell us how the body has rotated with respect to someone fixed on the ground. But since in this course we're dealing with time-stepping solutions, I think it's far more instructive to assume that the black coordinate system is the coordinate system at time step t. Of course, we can assume that that time is time 0, which would be the initial configuration. But in general, what we're going to be dealing with is rotations between one time step and the next time step, and how do we model rotations between successive time steps. So that said, I'm going to assume that the black reference frame, or coordinates, is the orientation of the object at some time step t. Now that we've got the red set of axes, which I will refer to as the primed axes, or the prime reference frame, let me reproduce that below. This is x1 prime, x2 prime, and x3 prime. And now we'll proceed similar to before, only this time we will apply a rotation to the coordinate system about the x1 prime axis. We'll call the rotation angle in this case theta 1. And as before, the axis of rotation remains unchanged. We're going to rotate the red coordinate system into the blue coordinate system. We will call the blue coordinate system now the double primed coordinate system, otherwise known as the twice rotated coordinate system. And in this case, the x1 double prime axis in blue is identical to the x1 prime axis, since the axis about which the rotation occurs doesn't change. But what does change is the position of the other two axes. I'll draw these in blue. So the x2 prime axis gets rotated there, and the x3 prime axis gets rotated, and we'll call these x2 double prime and x3 double prime. And similar to before, the rotation of these axes is now theta 1. Now, since we're absolute pros at doing this, I'm going to shortcut this. We want to write the x prime coordinate system as some transformation. Any matrix in linear algebra can be thought of as a transformation. We'd like to write this as a transformation of the x double prime axes. And I showed you before how to do this. Because we are rotating about the number 1 axis, the 1, 1 diagonal will get the 1. The remainder of that row will get zeros, and the remainder of that column will get zeros. On the diagonals, we're going to put our cosine terms, cosine theta 1 and cosine theta 1. and the off-diagonals will have the sign terms. Now, which sign term carries the positive sign and which is the negative sign? Notice that x2 is outside of the two blue axes, whereas x3 is in between the two blue axes. Therefore, x2 carries the negative sign. So in row 2, the off-diagonal sign term must have the negative sign, as indicated. And it's just that simple to write that transformation. That's equation 5. Let's put a blue box around it. We'll use that later too. Now finally, we're going to go through this whole process a third time. I'm going to reproduce the blue axes, going to label them x1 double prime, x2 double prime, and x3 double prime. And now we want to apply a third rotation, but in this case we're going to do it about the number 2 axis, or the x2 double prime axis. We'll assume that the rotation is by an amount theta 2. We will draw the new coordinate system in green. This will be the triple prime coordinate system, or the thrice rotated coordinate system. So the rotational axis remains unchanged, and we'll call that x2 triple prime. The x3 and the x1 axes get rotated into a new position. We'll label these x1 triple prime and x3 triple prime, and indicate that these have been rotated by an amount of theta 2. And then as before, we would like to write the double primed coordinate system in terms of the triple prime coordinate system. So x double prime is equal to some transformation times x triple prime. Where does the 1 go? The 1 goes in the 2, 2 position because we have rotated about the 2 axis. The remainder of that row gets zeros, and the remainder of that column gets zeros. The diagonal terms will get cosine theta 2. Just in the interest of saving space, I've written it as c theta 2. You should read that as cosine theta 2. And the remaining off-diagonal terms will get the sine theta 2 terms. Now where's the negative sign? When I look at the two blue axes, the theta 3 double prime and theta 1 double prime, I see that theta 1 double prime is between the two green axes, but theta 3 double prime is outside of it, and so the theta 3 double prime, or row 3, will have the negative sign. Call this equation 6 and put a box around that. Now at the point that I've committed these 3 successive rotations, the green reference frame can assume to be the state of the body at time step t plus 1. So to be clear, in moving from time step t to time step t plus 1, the idea of Euler angles is that the body goes through 3 successive rotations, about 3 principal axes, and only having gone through those 3 rotations do we arrive at its configuration at the next time step. The beauty of this is that Euler discovered that in fact a body can always be rotated from one orientation to another orientation by a set of 3 Euler angle rotations. Let me say that again. Starting at any position at time step t, using 3 successive Euler angle rotations, that body can be moved to any other orientation within 3 dimensions. Probably also a good time to mention that these transformation matrices, these 3 transformation matrices, are known as orthonormal transformations. The orthonormal meaning comes from 2 different things. First of all, it's orthogonal, and what is meant by orthogonal is that this transformation is really just a change of coordinate system, meaning that applying this transformation doesn't change any of the length of the vectors that it's transforming, these vectors, and also it doesn't change the angles between any vectors. That is to say, the dot products before the transformation and the dot products between 2 vectors after the transformation remain identical. The reason that it's not just orthogonal but orthonormal, orthonormal is a subset of orthogonal transformations. In other words, any orthonormal transformation is also an orthogonal transformation. But orthonormal transformations have the additional restriction that each of the columns of the transformation matrix have unit magnitude. If I take any one of these columns, well, certainly the last one here we can see has unit magnitude, but if I try to find the magnitude where I would just square each component and take the square root, I would get cosine squared plus sine squared. That's a trig identity, and it's 1. Square root of 1 is 1. And so the columns of each of these matrices have magnitude 1. Because of that, in addition to them being an orthogonal transformation, these matrices are also orthonormal transformations. The fact that these transformations are orthogonal is very important because it gives us the basis for being able to change coordinates while preserving the nature of the vectors in the space. So let's begin on the next page by examining this transformation here, the first one. On the previous page, we were able to write the x-coordinate system in terms of the x-prime coordinate system by multiplying the prime coordinate system by a transformation matrix. That transformation matrix, that took us from the primed or the number 1 coordinate system to the 0th coordinate system. No primes. So we will write that transformation in shorthand as T01. And the way to read this is the transformation to the 0th coordinate system from the first coordinate system. T01 transforms us from 1 prime to 0 primes. Similarly, we could write the x prime coordinate system as a transformation times the x double prime coordinate system, in this case T12, because it transforms us from the 2 coordinate system to the 1 coordinate system. And then similarly, we can write x double prime as a transformation times the x triple prime coordinate system, where we call that transformation T sub 2, 3, meaning it transforms from the 3 to the 2 coordinate system. Just a short, compact way of writing this. Let's give these numbers 7, 8, and 9. And now what I'm going to do is take equation 7, and for x prime, I'm going to substitute equation 8 in there. So I can write this as x is equal to T01 times T12 times x double prime. And similarly, I can substitute equation 9 in for x double prime. So making that substitution gives me that x is equal to T01 times T12 times T23 times x triple prime. Now using the same terminology in equations 7, 8, and 9 above, I can write this overall transformation as x T03 times x triple prime. Why T03? Because this is transforming me from the 3 coordinate system to the 0 coordinate system. So what's interesting about this is if we just compare these two equations, we can rewrite T03 as T01 times T12 times T23. So if we want to find a transformation to go from the 3 coordinate system to the 0 coordinate system, we just multiply the individual transformations together, and really what happens is the 1's cancel and the 2's cancel, and I'm left with T03. Similarly, if I wanted to find the transformation between the 2 coordinate system and the 0 coordinate system, that just comes from what I have up here. That's equal to T01 times T12. So these transformations provide us a very useful way of transforming between any 2 coordinate systems that we have, just by multiplying the appropriate transformations together. Let's give these some numbers. It will be 10, 11, 12, 13, and 14. And let's put some boxes around it because these are important derivations. Now, looking at equation 12 again, if I take equation 12 and I pre-multiply that by T03 transpose, in other words, the transpose of this matrix, what I get is that x, let me just write it out and then I'll explain it, x triple prime is equal to T03 transpose times x. Now what happens here, when I pre-multiply this by T03 transpose, I get the identity matrix. Why? Because an important property of an orthogonal transformation is that its inverse is equal to its transpose. So by multiplying here by the transpose, I'm actually multiplying by the inverse, and that gives me the identity matrix. I've left it out, but in fact, we should have the identity matrix here. And then I've just rewritten this equation by taking x triple prime to the other side. So on the left-hand side, which is now the right-hand side, I have T03 transpose times x. And on the right-hand side, these cancel because of our property of orthogonality. Let me just write that in here. Once again, one of the properties of an orthogonal transformation matrix, mathematically speaking, is that its inverse is equal to its transpose. So all I did in equation 12 is I multiplied by the transpose or the inverse, which cleared the T03 from in front of the x triple prime, and then I rewrote it in this form. But having rewritten it in this form, This transformation matrix T03 transpose is really taking us from the 0th coordinate system to the 3 coordinate system. So using the same nomenclature above, I could rewrite this as T30 times x. Why? Because we're going from the 0th to the 3rd coordinate system based on this equation. This implies, by looking at that T30 is just the transpose of T03. So, having got any of these transformations, if I want to go in the reverse direction, I simply need to take the transpose. And this is a very good result, it turns out. Number 15, 16, 17, and let's box our very good result. And again, I can get the overall transformation by multiplying each of the individual transformations together. And then if I want to flip the transformation, I can just take the transpose. And then, of course, this orthogonality property, that the inverse and transposes are the same. And by the way, if you don't believe me on that, just take the transpose of this matrix and multiply it by this matrix, and you'll see that that in fact gives you the identity matrix. Okay, moving to the next page, let's talk about the rotation sequence. In the example I gave you, I just arbitrarily made the first rotation about the number 3 axis, then the number 1, then the number 2. It turns out that the order, or that the sequence of rotations, is completely arbitrary, other than each successive rotation needs to be about a different axis. Now, for example, if we rotated first about the x3, then about the x2, and then about the x1 axis, if we had done it in that order, we would refer to that as a 3-2-1 rotation. Again, it's arbitrary, and we could have just as easily chosen a 1-2-3 sequence where we rotated about the x1, then the x2, then the x3 axis. It turns out you actually don't need to rotate about 3 different axes. For example, I could have rotated in a 2-1-2 sequence. So rotate about the x2 axis, then about the x1 prime axis, and then about the x2 double prime axis. I don't have to use 1, 2, and 3 in my sequence. And it turns out that any of these sequences, with the correct angles, can rotate me from any given orientation into any other orientation. But here's the thing. Whatever you decide to choose for your rotation sequence, once you've picked it, you must keep it in that order for the remainder of your model and for your problem. You can't do one rotation in a 1-2-3 sequence and then the next one in a 3-2-1 sequence. You've got to stick to whatever sequence you decided is going to be the order of your rotation. That is the most important thing about it. So let me re-emphasize that here, that order matters. Now, it turns out that when you have a 3-2-1 or a 1-2-3 sequence, when you have a sequence about the 3 different axes, these are in fact referred to as Tate-Bryan angles. Now, I must confess, until I started reading up some material before making this video, I had never, ever heard these referred to as Tate-Bryan angles. From my experience, everyone refers to them in the industry as Euler angles. There might be some haters out there that are screaming at me saying, I can't believe you said that, but I've got to be honest, I've never heard them called Tate-Bryan angles. They've always been known to me as Euler angles, rightly or wrongly so. It turns out that a sequence like 2-1-2, where one of the axes is repeated, that's in fact an Euler angle sequence. But again, I don't think anyone is going to come after you, certainly not in my experience, for referring to all of these as Euler angle sequences. Now, it turns out that these Tate-Bryan angles are generally used in aerospace applications, where the sequence like a 2-1-2 sequence is generally used in objects like a spinning top, where the 2-1-2 sequence would refer to precession, nutation, and rotation, or spin. So let's look at an aircraft as an example. And in various applications within and around aerospace, people have various ways of labeling their axes. Of course, up till now, we've always looked at beams, which could be wings, in which the x-axis typically runs along the elastic axis of the wing. However, when one looks at controls and dynamics of whole aircraft, typically the x-axis points through the nose, and the y-axis points down the right wing. And then, of course, because we want a right-handed set of coordinate systems, the z-axis will point vertically downwards. In the case of an aircraft, generally we refer to the roll angle, the angle about the x-axis, as phi, We refer to the pitch angle, or the angle about the y-axis, as theta, and we refer to the yaw angle, or the angle about the z-axis, as psi. And let me just redraw the coordinate system for clarity, that in the context of what I've presented up till now, I would refer to the x-axis as the x1 axis, the y-axis as the x2 axis, and the z-axis as the x3 axis. And just to remind ourselves, this is roll, pitch, and yaw, phi, theta, and psi. And what would this sequence be in the case of roll, pitch, yaw if I did it in that order? Well, roll is about the 1 axis, pitch is about the 2 axis, and yaw is about the 3 axis. So if I were going to apply the Euler angles in the sequence of roll, pitch, and yaw, that would amount to a 1, 2, 3 sequence. That it turns out that in a lot of aerospace applications, it's actually a 3, 2, 1 sequence that's used. So yaw, pitch, and roll. In other words, for the Euler angle rotations, you'll first apply the yaw, then the pitch, then the roll. But as I just got done explaining to you, it's completely arbitrary. And for whatever reason, all my life, I've always used a 1, 2, 3 sequence. Why? Because 1, 2, 3 seems obvious to me. And roll, pitch, yaw in that order just seems to roll off my tongue, maybe from years of practice. But I tend to use a roll, pitch, yaw sequence when dealing with rotations of aircraft. You want to pick another one? Go ahead, knock yourself out. It's no problem. Just remember, once you pick it, stick with it. So it's generally in your best interest to use the same sequence for all your projects because you're less likely to mess it up that way. However, you might pick up a project that someone else has done, in which case the first question to be sure to ask yourself is what is the Euler angle sequence that they're using? Okay, so finally, putting it all together, if I take my preferred 1, 2, 3 sequence with angles phi, theta, and psi, then I can calculate T03. A reminder, I'm just multiplying the red, the blue, and the green matrices together. In this case, theta 3 will be psi, theta 1 will be phi, and theta 2 will be theta. And when I do that, I get the following matrix, where for shorthand, C is cosine of the angle and S is sine of the angle. If you picked a different sequence, then your overall transformation matrix, the T03 matrix, will look somewhat different from mine. Number 18. I can rewrite this transformation matrix in general form as the following, where I've used a lowercase t because I didn't want to confuse it with t for transformation. But I've really just indicated with a lowercase t each of the components. And I want to make the point that if you have been given this overall transformation matrix and you want to figure out what your Euler angles are, you can figure it out in this case by looking at this matrix. For example, if you know what T13 is because you've been given this whole transformation matrix, then you can get theta from here, for instance. That's just the arc sine or the inverse sine of T13. Similarly, I'm just going to write it out. And if you want to prove it to yourself, you can, as my professor used to say, when you're shooting pool, do it on the back of a napkin. That phi is equal to arctan of minus T23 over T33. Theta, as we said, is the arcsine of T13. And psi is the arctan of T12 divided by T11. And why do I want to give this to you? Because you're going to see in a later section that sometimes, depending on the method you're using, it's actually easier to come up with this complete transformation matrix, T03, and from that you might want to find the Euler angles. So this would be the method to do that. Number 19 and 20. And let's put a couple of red boxes around these because these are important results. Okay, so that's pretty much what I wanted to say about Euler angles. But before we go, and just to expand on this topic a little bit and maybe to galvanize your understanding, let's have a look at omega, which I'll call the rotational rates, versus Euler angles, or really Euler angle rates. Now, what do I mean by this? In many aerospace situations, you're going to have an onboard device, which is an accelerometer and a gyro, commonly referred to as an IMU, or an inertial measurement unit. And the gyros in this unit will tell you what your different angular velocities are. So you've got an aircraft or a spacecraft, and it's got a device on board that's sending out a telemetry stream, and it says, this is the instantaneous roll rate, this is the instantaneous pitch rate, and yaw rate. So we'll call this omega. Omega is the rotation rates. And in general, I can write omega as omega 1, omega 2, and omega 3. And these come from an onboard IMU, or specifically the gyro part of an IMU. Now, my question to you is this. If I find that a vehicle has a certain yaw rate, pitch rate, and roll rate, are these the same as the rates of change of the Euler angles? Let me say it again. Is the instantaneous roll, pitch, and yaw, as measured by a device on the aircraft or on the vehicle, are those equal to the Euler angle rates, the rates at which the Euler angles are changing? Maybe just pause the video for a minute and give it some thought. Okay, so the short answer is these are not the same. Why? Because it is assumed that an onboard device is measuring instantaneously the roll, pitch, and yaw rates. It's measuring them about the instantaneous body axis. So whatever the body axis is at time t, the time of the measurement, you should assume that the roll, pitch, and yaw rates are about those axes. In other words, what we would call the zeroth coordinate system, or what I referred to as the coordinate system at time t. So this is the coordinate system before it's been rotated, otherwise known as the body fixed coordinate system at time t. And we want to somehow relate that to the change of the Euler angles, or Euler rates as we call them, for phi, theta, and psi. Now, we know that phi dot, which is just the derivative of phi, is measured in the zeroth coordinate system. This according to a 1, 2, 3 sequence, which is the sequence that I have arbitrarily chosen. The phi angle, which is the first rotational angle, is in fact about the axes at time t, or the unrotated axes. Once I've rotated it by phi, then the theta coordinate system is actually about the number 1 axis. In this case, the x2 axis, but in the primed coordinate system. That's what I mean by the number 1 axis. Not the x1 axis, it's the x2 axis, but the once rotated x2 axis. And then similarly, psi dot is rotated about the x3 axis, but in the double prime configuration. All right? So the difference between the omegas, well, there's no difference between omega 1 and phi dot, because those are about the same axes. But omega 2 and omega 3 are not equal to theta dot and psi dot because we've got different coordinate systems. So before we can compare them, what we need to do is convert from the 1 and from the 2 coordinate system back into the 0 coordinate system. Okay, so these are the Euler rates. Let's give it a number, 19 and 20. Now we know how to transform vectors back to the 0th coordinate system because we did that before. Of course, we don't need to do anything with the phi dot. That's already in the 0th system. But the theta dot, we just need to multiply by the transformation t01, which transforms from the 1 to the 0 coordinate system. And then similarly, in the case of psi dot, we'll use 202 to go from the 2 to the 0th system. Now, what you find is if you multiply this all out and you collect coefficients of phi dot, theta dot, and psi dot, you end up with something that can be written in the form of some transformation t times phi dot, theta dot, and psi dot. 21 and 2. But since the object of the exercise is to find the Euler angle rates, I want to rewrite this by taking the inverse and saying that phi dot, theta dot, and psi dot is just the inverse transform times the omegas. Now let me ask you this. Is this inverse transform equal to the transpose? Can we take the transpose instead of the inverse? The answer is no. T is not orthogonal in this case because we didn't multiply these matrices together like we did before. When you multiply orthogonal transformations or orthogonal matrices, the result itself is an orthogonal matrix. But we didn't multiply these together. What we did is we actually multiplied it out and then collected coefficients to get to this form here. Okay, so number 23 in this case, T is not orthogonal, and therefore T inverse is not equal to T transpose. Don't sweat too much about what I did on this page. I would just like you to have seen this before. I think this will be especially interesting for those of you who maybe play around with drones or are interested in somehow taking a telemetry stream and representing a vehicle attitude on a computer display. So don't sweat it too much if this went a little bit over your head, but if it didn't, that's great. Power to you. And before ending this section, I think one thing I'd like to mention to you is one of the problems that's commonly associated with the Euler angle method, and that is something known as Gimbal lock. In the event that your second rotation, whatever it is, whether it's about the 2-axis or the 1-axis, if that rotation is 90 degrees, you get a condition known as gimbal lock, which results in you losing a degree of freedom. Imagine it in the context of this aircraft. For example, if the roll angle was 0, and then I pitched it 90 degrees, now the roll axis aligns with the yaw axis, and you can't really distinguish between rolling the aircraft or yawing the aircraft. This is a problem that we don't generally find in a time-stepping solution because as long as your time steps are small enough, it's unlikely for most situations that you'll be dealing with that your object is going to rotate by 90 degrees between two successive time steps. However, if you're comparing the orientation of the object to an inertial reference frame, then certainly gimbal lock is something you need to be aware of. One of the real benefits of using the Euler angle method is that we only need 3 parameters to describe the complete rotation. And these are the 3 Euler angles. And also, it's somewhat intuitive. One can picture what's going on in terms of these 3 successive rotations, as opposed to when we look at the overall transformation where we're not really sure how things are rotating. Well, this video has run quite a lot longer than I would normally have liked, but it was important to get all this information in one place. So I will cut the video in the end of part 1 at this point. I promise the following parts will be much shorter, and when I'm done with all 4 parts in this mini-series, then I'll give a comprehensive review on all 4 parts from the beginning. That said, I hope you found something useful in this video. If you did, please go ahead and hit those like buttons, or better still, subscribe to this channel and click on the bell icon to be notified of future video releases. If you have any questions or comments, I'd love to hear from you in the comments section below. The lecture notes for this video are available using the link in the video description below. Thank you very much for watching, and I will catch up with you in the next one.